Hello, Vanguards. I have a brilliant idea today. Let's talk about light. The topics that we want to cover are how light interacts with matter, the spectrum types that we use in chemistry, and some of the basic properties of light. The first thing that we need to do is understand three concepts, and they are transmission of light, absorption of light, and reflection of light. In the first instance, you have a white light, and then you have a liquid, in the first case a blue liquid, in the second case a yellow liquid, and the diagram shows what happens to the various types of light that shine upon it. Well, in the first instance, we have a copper compound, which is blue, so it's a dissolved blue compound, and if we shine yellow light at it, the yellow light does not seem to make it through. If we shine blue light at the blue substance, the blue light does go through. And if we shine white light at the blue liquid, only blue light makes it through. So what's happened to all the other colors? The red, the orange, the yellow, the green, the indigo, and the violet. See how I skipped blue? If we look at the second example, we have a yellow compound, and yellow light seems to go through, but blue light does not go through. And apparently all of the other colors, the red, orange, yellow, green, red, orange, green, blue, indigo, and violet, do not go through. So what we say is that because the blue light does go through the first solution, it's being transmitted. Because yellow light does not go through, it's being absorbed by the blue liquid in the first example. Assuming that white light is made up of all colors of the spectrum, all the other colors are absorbed except for blue, and blue makes it all the way through. Now the last thing is reflection of light, and so reflection is like something being reflected in a mirror. So if I turn on the light again from over on the side here, and if I put the blue solution back behind the light bulb is giving off all colors of the spectrum, and the light is coming here, hitting the blue solution, and it's bouncing back and hitting you right in the eye. In chemistry, we consider three different spectrum types: continuous spectra, which is the plural of spectrum, emission spectra, and absorption spectra. Continuous spectra are those that come from hot solids. Inside of the light bulb, there's a very, very hot tungsten filament it's a solid. It's giving off a continuous spectrum, all colors of the rainbow. The second kind of spectrum that we're going to consider is called an emission spectrum, and this comes from a low pressure gas. So there's a special kind of bulb that we can buy, and this bulb is filled up with just one kind of gas. This one's filled up with neon gas. And if we put some electricity through the neon gas, this gas, which is under low pressure, there's not very much of it inside the bulb, and we turn it on, we'll see a really, really cool result. This is called an emission spectrum, and if we were to look at this through our spectroscopes, we would see a spectrum that looks like this middle one. There are bright lines every so often. Sometimes it's called a bright line spectrum. The third type of spectrum that we'll be looking at is called an absorption spectrum. It's almost a continuous spectrum or a complete spectrum, but they're missing wavelengths. These are wavelengths that are being absorbed. The next thing that we want to do is consider light itself. What light is made up of, and how it travels, and how to measure it. Instead of saying light, sometimes we say electromagnetic radiation, because electromagnetic radiation considers all the different types of light, from radio waves to visible light, which we can see, to ultraviolet, to gamma rays, and some other types as well. Light, or electromagnetic radiation, is apparently made up of things called photons, which are weightless particles that travel at the speed of light. They're called photons. Don't confuse them with protons, the things in the nucleus that weigh 1 AMU. These are photons, as in photo, which means light. We consider the electromagnetic spectrum, the entire spectrum, and that goes all the way from radio waves to gamma rays. And you can see some of the different types of electromagnetic radiation listed over here. Down below, you can see what their waves, relatively speaking, look like. Longer waves, shorter waves, that kind of thing. So as we do some of our calculations with light, we'll need to understand three parameters. And these are speed of light, which is given the letter c, as in E equals mc squared, Albert Einstein's famous equation. C is always 3 times 10 to the 8th meters per second. It's always really, really close to 3 times 10 to the 8th meters per second. The second thing is wavelength, and wavelength is given the Greek letter lambda, which gave rise to our letter L, but it looks a little different. Practice making that a few times. Wavelength, or lambda, is meters, or more precisely meters per cycle. And the third thing is frequency, and the symbol is called nu, and it looks like a V but with a little tail on it. And nu, or frequency, is the cycles per second, or hertz, how often a wavelength occurs. The famous equation, which we will be using, is C equals lambda times nu. By looking at this equation, you can see that nu and lambda are inversely proportional. Let's do a little bit of practice with waves. So here are several different waves. We have a wave up on top, which is like this. This is a long wavelength. And way down here at the bottom, this is showing a short wavelength. Wavelength is from the top of a wave to the top of a wave, which actually is the same as the distance between the bottom of the wave, or the trough of the wave, and the trough of the next wave. Or you can even go half down to halfway down if you really wanted to be a smart aleck about it. So that's a wavelength. Here's some quiz questions for you. Which of these electromagnetic waves has the highest frequency, which would have the most cycles per second, or the highest hertz? And the answer is the bottom one has the highest frequency. Which one has the lowest frequency? That would be this top one here. This has the lowest frequency. The next question is, which one has the longest wavelength? So I think that's pretty clear that this top one has the longest wavelength, or lambda. Let's get used to using those symbols. Which one has the shortest wavelength? That's the bottom one again, from the top of this wave to the top of this wave. This distance down there, that's a very short wavelength. And now the last one is a trick question, so beware. Which one has the greatest velocity? If you had 1, 2, 3, 4, 5 different flashlights, and each one gives off a different kind of light, and you were somehow or other able to turn them on at exactly the same time, ready, go, they would all reach this point at exactly the same time. Let's take a look at what we talked about today. First, we considered transmission, absorption, and reflection of light, and what they meant. Then we looked at the 3 different types of spectra: continuous, emission, and absorption spectra, and what they might look like. Continuous spectrum, all the colors of the rainbow. An emission spectrum, where you just get certain colors. And an absorption spectrum, where you see all the colors of the rainbow except you're missing a few colors. And then the last thing, we're getting ready to do some calculations about light, and then we're going to use these calculations to tell us about chemicals. For this, we needed to know what photons were. We needed to understand that the electromagnetic spectrum consists of all the different types of light, not just the visible light, the Roy G. Biv, which is down here. We learned about the speed of light, which is given the letter c. Value is always 3 times 10 to the 8th meters per second. We learned about the wavelength, or lambda, L-A-M-B-D-A, meters, or meters per cycle, how long this distance is from the top of one wave to the top of the next wave. And finally, we learned about frequency, or nu. Frequency has units of cycles per second, the number of waves per second. This is also given the value of hertz. We also introduced the equation that we'll be using, C equals lambda times nu, where C is the speed of light, lambda is the wavelength, a light wave, and nu is the frequency of that wave. Thank you, everybody.